This is StarTalk, Cosmic Queries Edition. I got Chuck Nice, my co-host, Chuck.
Hey, Neil, what's happening?
Chuck, this is grabbag.
It is indeed. We used to call it the Cosmic Potpourri. We used to call it Cosmic Gumbo, which was my favorite. Galactic, not Cosmic.
Galactic Gumbo.
Galactic Gumbo, which was my
alliteration.
favorite. But now we have a grab bag, which it makes me wonder, where does that come from? Grab bag. You know, it means just like an assortment of pretty much miscellaneous items.
Yeah, it's the presents in the holiday season where you reach in and grab and you don't know what you're getting.
Is that really what it is?
From Santa Claus. Why wouldn't it be?
Okay, cool.
Yeah.
Yeah, we called that Christmas.
You've been in my office. I have a grab bag in there that's a black hole.
Right.
It actually says black hole on the side of it.
Black hole, right. It is.
It says black hole. That's how you know it's a black hole. It says it.
Very nice. Very cool.
That reminds me of, completely off topic, but the discoverer of Pluto, his name is Clyde Tombaugh. My boy lived deep into his 90s,
right?
And because he wasn't letting go of Pluto any sooner than he
was hoping that it would happen.
He was trying to keep it.
Yeah, on his deathbed, they told him, "You did it. It's a planet," and he was just like, "Oh, thank God." And why'd you lie to him? He's dead. He's dead. He's dead. What do you mean, why did I lie to him? That's like somebody's dying and you say to him, "You know I never loved you." Right? No.
Long time to report that information.
Exactly. It's like he's dead. Like, let him, I loved you so dearly my entire life. I shall miss you. And then they die and you're like, "Oh, thank God."
So he was asked, what did it take to discover Pluto? How hard was that? And he said, well, when I got the photos of the night sky, it was really easy because there was an arrow pointing to it.
Oh, that's hilarious.
Because every picture you've ever seen of Pluto,
there is an arrow. That's funny.
So there you go. All right, so let's do this. Grab bag. I assume that's anything right. Under the sun and above it as well.
There you go.
So let's go for it.
Okay, now that makes me think the first question.
Well, just to remind people, these are all from Patreon members. Yeah.
And if you would like, please go to patreon.com/StarTalkRadio. Support us. And our lower level, that's the wrong way to say that.
Entry level.
Our entry level, thank you, Neil. Mm-hmm. Our entry level members, you get to ask Neil a question on our, and the reason we did that, one, is because Patreon is a great way for us to experiment and try things because you're supporting us financially. But more importantly, we were getting like 15,000 people asking questions. And so this is a great way to cull it down. So we're not asking you to pay for your questions, but in return for your gracious support, we ask a question.
Which sounds like they're paying for the question. But
all right. See, and I knew you were going to do that.
No.
I tried to NPR this, Neil. I tried to NPR
this. You were smelling NPR the whole way.
Okay. You pulled a chuckle on me. You were like, yeah, and you're paying for it.
All right. I shouldn't hang around you for so long.
Oh, my God. All right, here we go.
Give it to me.
This is David Bryan Smith. And he says, yes, this is really my name, not just made up. So actually, you can pronounce it, Chuck. Oh, you jerk. I should read these in advance. All right, David, you got me. He says, can you explain the moon's wobble and how it affects the Earth? Interesting. Okay.
Well, so I don't think he's referring to the moon's wobble because that's not interesting. What's interesting, there's something called a libration. Not libation. Don't confuse it.
Is it anything like a liger?
No.
Okay. A libration.
A libration, right. Mm-hmm. You mean liger, like the cross between a lion and a tiger?
Yeah, you ever see those things? They're huge.
Yeah. No, this has nothing to do with that, Chuck.
Well, I just heard lie.
Okay. A libration. So what's happening is the moon's orbit, again, I'm assuming that's what he's referring to because the moon doesn't have a wobble that anyone cares about. So that's why. But there's an interesting libration. So what's happening is because the moon's orbit around the Earth is not a perfect circle, Okay, it's an ellipse. It can get as close as 225,000 or so miles, and as far as almost 250,000 miles. So there's a 25,000 mile range between when it's closest and when it's farthest. Okay. The moon is also tidally locked to Earth, so it's always showing the same face. Okay? That's a natural phenomenon in the universe. And systems of orbiting objects naturally descend into that state relative to each other. So that's fine. Nothing weird going on there. Here's the problem. Okay, if it were a perfectly circular orbit, you would only ever see exactly the same side, and it's locked. You'd only ever see exactly the same side towards you. Okay, here's the problem. When your orbit is not circular, when it's elliptical, you are moving faster in your orbit when you're closer and slower in your orbit when you're farther away.
Okay.
So the point is, if you are tidally locked and in a perfectly circular orbit, for every little bit around the Earth you revolve, you will rotate a little bit, always keeping that same face pointed. So everything works out. But if you're going a little faster than average or a little slower than average, that little bit that you rotate doesn't line up as it would if you were in a perfectly circular orbit. It lines up on average. Mm-hmm. But if you're sort of fast in your orbit, then that little bit that you turn doesn't quite compensate for how far you've gone around the Earth. And if you're slow in your orbit, you haven't quite turned enough.
Right.
So when you look at time-lapse photos of the moon, it is striking to behold. The moon is like it's like turning a little to the left to you, a little to the right. So we can see more than 50% of its surface over the duration of a month.
Okay.
Month. Excuse me.
A month. I like that better. It's the month on the moon.
That's the original word, of course.
Yes, a month.
So
yeah. Well, go ahead.
Yeah. So, and yes, to the extent that there's a wobble and anybody cares about it, that's true anytime you have a rotating object where it's not perfectly spherical. If there's a slight bit of mass off to the side, then there are extra torques on it, and that'll sort of bob as it turns. We wobble on our axis because of forces that are tugging on us, such as the moon, as we rotate and as we go around the sun. So you do get this sort of wobbling and bobbing. But for me, the fun thing is the libration. If you just Google libration of the moon and look at the time-lapse video, it's striking because you don't get to see it that way, because we see the moon once a night, or once a day, and when you time-lapse it for a month,
so it's kind of like the face that it shows us just turns a little bit.
Yeah, exactly. I should thank you. That's way easier. Yeah. That's what I should have done. It got a little to the left,
right? A little to the right. So it's like when it's 25,000 miles out, it's like Le Tigre, and when it's like right close to us, it's like blue steel. So.
And I even know what blue steel means. That's embarrassing. Okay.
Not really. That's not really embarrassing. You were in the movie.
I was in Zoolander 2. That's right.
That's right.
And I did do a blue steel imitation. I did. In fact, it's the very final thing you see in the movie. And I am the last thing you see in the movie Zoolander 2.
And anyone listening, please go look at that.
No, don't. Please don't look at that.
Please go look at that. Because I believe you're wearing a fur coat too, which is
it's a shoulder wrap fur. It's not. I don't think it's a full coat. I think it was just something around my upper shoulders and neck.
Yeah, like a they call that a stole back in the
stole.
day.
It was a stole. Right. Yeah. And then I sort of turn my head and then I give the expression. Just to be clear, Chuck.
Yeah.
Okay. I've been in 4 movie franchises. Okay. And for 3 of them, there were no more movies made after the one I was in.
Okay, that's pretty damn hilarious.
Okay, so I was in Ice Age 5.
Okay,
and the critics said it's about time the series went extinct like all the creatures in it.
Oh, damn. Oh, my
I
God.
thought it was a pretty good movie, though, because it had a lot of science in it. So I was science biased. That's why I was one of the characters. Mm-hmm. So that was the last of the ice ages. I was in Sharknado 6.
Okay.
You didn't know there were 5 others, did you?
Well, I did not, number one.
Okay.
And I'm so glad to hear that there's not a Sharknado 7. I'm just saying.
So, unlike the Fast and the Furious...
could you please be in that? Please be in that.
No, but I don't want to kill the franchise.
I do, and that's why I want you to
no,
get
that's
it.
why you want... you want me to so that the franchise dies.
Exactly. Okay. I just want the last scene to be you, like, cruising, like, yo, what up? Keep looking up, but not while you're driving.
Not while you're driving. All right, give me another question.
Okay, here we go. Zach Metcalf wants to know this. Good morning, gentlemen. Have anatomically modern human beings always lived under the same night sky? Have the stars had time to migrate and rearrange themselves in approximately 150,000 years that we've been looking up?
Love that question. So first of all, the dude knows that however fixed the stars look like they are on the night sky, in fact, they are moving through space. And obviously, the farther away something is, the less from day to day you're going to notice that it's moving. Right? So that's true on Earth as well. Right. This is what led to the old childhood concept where you say, Mommy, Daddy, why is the moon following me?
Right.
As you walk down the street, because the trees go by and the buildings go by and the moon is just there. Well, if you kept walking for 1 million more miles, you would leave the moon far behind. So you're just not walking far enough for something that distant to reveal the fact that you're walking past it. So the farther away something is, the less obvious its motion is to you. Okay? So so we have all the stars in the night sky, and they are part of the solar neighborhood. How's that for a friendly phrase that we use?
It.
It's solar neighborhood.
You're now the Mr. Rogers of the cosmos.
Welcome to the neighborhood.
Yes. Hello, neighbor.
Hello, neighbor. Oh, you're about to explode as a supernova. Oh, let me get the hell out of the neighborhood. Okay. That would be an interesting.
Excellent.
All right. So we're all orbiting sort of the center of the galaxy together, but even with that sort of community movement, there is movement among us. Okay.
Right.
So if you go back 75,000 years, we were anatomically human. I think that's sort of early Homo sapien. 100,000 years ago, you would not recognize most of the constellations of the night sky.
What?
That's right. That's right.
Oh, man.
Well, not most. I would say about half. The stars that are nearby us that trace out the constellations, they'd be in a completely different place. So, for example, the Big Dipper, which we know of as looking like where is it? In England, is it called the big saucepan?
The big ladle?
The ladle. The ladle
ladle
is the Little Dipper.
Right.
The Little Dipper, the handle bends the other way like a ladle would. Okay. And the Big Dipper. Point is, all the stars of the Big Dipper, believe it or not, are part of a coherent star cluster, which is really close, so you don't think of them as a tight cluster. But so they're all sort of together, and they're moving in their own sort of orbits, and the Big Dipper would get flattened out, it turns out. We've done the math on this.
Wow.
You just wouldn't recognize it as a Big Dipper at all. Okay, go on.
Terracina, no last name, like Cher, just Terracina. And Terracina says, hey, Neil, hey, Chuck, why is Mercury the element? Okay. Very nice clarification there, Terracina.
Because she's talking to an astrophysicist, you got
to make that clarification, yes. She says, why is Mercury, the element, liquid? The elements before and after it in the periodic table, gold and thallium, are both solid at ambient temperature. So why does one proton make such a difference?
Ooh.
Oh, I love that question because I have no idea why.
well, I'll get to that question when we return after our first break on StarTalk Cosmic Queries. Chuck, we're back, Cosmic Queries.
Okay.
Grabbag.
Grab
Questions
bag.
coming from everywhere.
Yep, that's right.
Kind of left field, right field, behind home plate.
That's when you know a fan is mad.
Oh, if it comes from behind.
If it comes from behind home
No, if they
plate.
throw at your head, then they're mad at you.
Yeah, exactly.
So this last question was from Terracina. Well, who is this?
Yep, Terracina, who says, "Hey, Neil, Chuck, why is Mercury the element liquid? The elements before and after in the periodic table are both solid at ambient temperature. So why does one proton make such a difference?"
Okay, I can answer that. I don't have a good idea. I don't know.
Wow. Okay.
Well, I mean, I can fumble through an answer. Okay, right. I will give you an answer, but it will be wholly unsatisfying because I don't have a deep understanding of it. But I can give you an answer, and here it is. You ready?
All right.
Okay.
Because I said so. Because it's nature.
Thank you, Chuck. Next question.
Yeah.
Thanks for
Did
helping me out.
That clear it up for you? It's nature.
Crystal clear.
There you go. All right, go ahead.
So you say, how could only one proton in the nucleus make such a difference? Because you're comparing what was to the left of it and to the right of it on the periodic table. And the periodic table is an ascension of proton count in the nucleus of atoms. That's what that is. And you go from hydrogen at number one proton, up to uranium, 92 protons, and then the elements we create in the lab goes up to, I forgot what they're up to now, 120, something like that.
That's just,
wow.
Wow.
So it turns out, remarkably, and we didn't really understand this until quantum physics in the 1920s, which gave us an understanding of how it is that you have periodicity in the properties of elements on the table. Okay? So you have to ask.
I'm certainly going to start a band called Periodicity.
Periodicity.
Because I never heard that word before until
periodicity.
Just now.
You never heard that. Okay.
No, periodicity.
So what we learned from applying quantum physics to the periodic table is that vertically on the table, elements have properties, chemical properties, similar to each other. So where you find carbon, for example, you look directly, what's directly below it, it's silicon. And so we're carbon-based life, so everyone is eagerly looking for silicon-based life. If carbon can make life in all these molecules that comprise life as we know it, silicon sitting right below it makes the same families of molecules as carbon does. And so elements in vertical columns, we've learned how and why that's so from quantum physics, has similar chemical properties. But the melting point is not a chemical property. It's actually intrinsic to the element itself. And so what happens when you change it, then the charge changes in the nucleus of the atom. And that changes the electron orbitals in response to it. Not orbits, but orbitals, we call them. Inspired by the orbits of planets, by the way, because we thought maybe you have solar system with the sun in the middle and planets in orbit around it. As we start poking the atom, we say, it's got a nucleus and it's got electrons. Maybe it's the same thing, but just little.
Right.
And it's not. Whole other laws of physics apply there. And it's the realm of quantum physics. So, point is, Mercury melts at about 40 degrees below zero. And so it's liquid that all degrees above that until it evaporates. And that's a unique property. So many elements on the periodic table have unique properties relative to everything around them that it's one of the reasons to celebrate that it exists at all. And it's a testament to the genius of chemists and physicists who go into those elements and say, this has this property, so I want to do this other thing with it. This conducts electricity. This does not conduct electricity. This is brittle. This is flexible. This is gaseous. This is liquid. And so we've gone all into the periodic table and basically constructed civilization based on it. So I don't have a good answer for you because I don't know what to tell you about why that's liquid and nothing around it is, left or right or up or down. But I can tell you being liquid is not the most different thing about an element that you can find among elements on the periodic table.
Wow. Okay. So
and by the way, if we lived in a world that was 50 below zero,
right,
you wouldn't be asking this question. Mercury would be solid like every other element.
Right.
Okay? We can go to a warmer environments and you'd find some things that then become liquid, and you might be asking that about those other elements.
Right.
So the fact that we are okay in these, quote, room temperatures has consequences for which elements on the periodic table are solid, liquid, or gas.
Wow, that's very
So that's
cool.
me dancing around the fact that I don't actually know the answer to that question.
Okay, so for somebody who... I'd hate to know what if you knew the answer. God, we'd be here till next year if you actually knew the answer.
What I'll do is I'll do some homework on it, and I'll come back and see what I can tell about the relationship of one mercury atom to another, and why it is that at this temperature, unlike every other metal on the periodic table, that they don't make a solid lattice. I'll find out, and I'll get back to her.
All right. Well, thanks, Teresina, for giving Dr. Tyson some homework.
Yeah, okay.
All right, let's, here we go. This is...
Oh, by the way, there's an element, and I forgot which element. Forgive me. I'll dig it up the next time I return. There's in the UK, the ambient indoor temperature, lab temperature, is slightly lower than in the United States or in Germany or in France. And so when the UK folks made their periodic table, there's an element that they listed as liquid, but in the United States and France and everywhere else, it was listed as listed as solid, but for everybody else, it was liquid.
Wow. And,
yeah,
and
so
just from a slight variation in the lab.
Yeah, just because the ambient lab temperature in England is about 5 degrees cooler than the ambient lab temperature in other sort of industrialized states at the time. So the point is, if you want to think of the periodic table as some fundamental truth about the universe, then you should not be distracting yourself with what temperature it melts, because that can depend not only on the individual if you want to think of the periodic table as some deep fundamental truth about the universe, then you should not be distracting yourself about whether it's solid, liquid, or gas at your laboratory temperature. Because the universe doesn't give a rat's ass about your laboratory temperature. That's not a fundamental truth about the element, whether it's liquid in your lab.
Yeah, there you go. Don't you know who I am? I'm the universe.
Thank you.
You want me to think what? What you say? You cold? You need a sweater? I'm the universe. Are you kidding?
That's right. Yeah. So
you think this is cold? I'm at an absolute zero. A couple degrees above it all the time.
And you know the methane that comes out of your stove if you use a gas stove?
Right.
On Earth, that's gaseous. You go to Saturn's moon Titan.
Right.
It has the right combination of temperature and air pressure to liquefy methane.
Swimming in methane. That sounds like a dream.
and the water, it is so cold that the water has frozen so solid that it's basically the bedrock on the planet. They're boulders and it's just ice. But those are the rocks. And think about it. Inside a volcano, what happens to rock?
It melts.
It melts.
Well, yeah.
So if we're in an environment that's as hot as a volcano, you would not think of rocks as anything solid. You'd say, oh, that's a liquid. Let's take a bath. And so these conditions that you happen to live in are not themselves fundamental to what's going on the periodic table.
Wow, there you go. All right, Teresina, we got more out of that than I ever thought for somebody who said that I don't know.
Okay.
Only physicists and astrophysicists answer questions that they don't know for 6 minutes. All right, here we go. Uh-huh. This is Jordan Belicanis. He says, hey, Dr.
Oh, wait. One other thing.
Okay.
There are places on Mars where the temperature and the air pressure, the atmospheric pressure, are just right. That water, if you live there, water would freeze, melt, and boil all at the same time.
What? Okay.
So you can have a bowl of water with ice cubes in it, and the water is boiling, and that's stable.
That's pretty Okay, I don't. I was going to say that's hot, but it's not. So
it's not.
And I was going to say it's cool,
point.
but it's okay. That's hot and cool, and that's everything.
That's everything to say. It's not hot. It's good. It's not tepid, right? So it's called a triple point, and water has a triple point of atmospheric pressure and temperature, where all states, 3 states of matter, can coexist happily. And so, yeah, that's why you can say water is liquid. No, water is only liquid when you make it a liquid. Okay.
Right.
Otherwise, it's solid or gaseous.
All right. Cool.
There you go.
All right. Jordan Belcanis. Yep. He says, "Hey, Dr. Tyson and Chuck, what's happening? I never have been able to understand the thought of terraforming Mars. Considering, listen, here's the real thing. It's a dead planet with no magnetic field. It seems solar wind and extreme UV would strip the atmosphere and kill any life anyway. Can you please help explain how this would ever work?"
Okay, so he's 2 steps ahead of someone who might have only just now heard of terraforming. So terraforming is you take a dead planet and then you seed the atmosphere with aerosols, or you introduce microbes that will thrive on the carbon dioxide and might output oxygen, and then you step back and let it run its thing if you put in the right cocktail, and then out comes an arable green planet that you just terraformed. That's not an impossible dream, okay? It's not. I mean, Earth was terraformed early on by Earth itself, right? So the question is, can you do it like fast? If you have to leave Earth, you got to find another place.
And they did it in one Star Trek movie.
They did in the movie. Yes. It was the
Star
Genesis
Trek movie. The Genesis. That's what it was called.
The Genesis Project, right? They took some pod or something and sent it down, and
right.
I think
it
it was
began
a
a
pod.
train
No.
reaction.
The pod was somebody's dead body that then came back to life.
Oh, okay. Spock. Yes.
It was Spock. Yeah.
Cool.
Okay, so you're worried. The who is this now? Jake?
This is Jordan. Jordan says, yeah.
So Jordan is worried that because Mars does not have a magnetic field, which would then shield it from solar wind, whose energy can break apart molecules, or have ozone that would protect it from ultraviolet. All of these, without these protections, life on Earth, we don't know how you would sustain it. Okay, that's fine. Consider that if you're living underground, none of that matters.
Oh.
Or
there you go.
You shield yourself from the sun, none of that matters.
Martian Morlocks.
I forgot.
Yeah, Martian Morlocks. That's what we got.
So, first of all, you can just shield yourself from it. Second, if we have the power of geoengineering to turn Mars into an arable place, I don't see why we couldn't figure out some way to deflect the solar wind or to block out UV. I'm not worried. That's like an engineering challenge. And engineers tend to solve problems when given the task. And so I'm not worried about that. It's the rest that is way more complex. We know how to block UV. We know how to block the solar wind. We don't know how to send in microbes and come back 10 years later and have a forest. We just don't know how to do that. That's where the challenges are right now.
Gotcha. So we got the sunscreen covered. So
exactly.
that part's good.
Yeah, we good. We good.
All right. Okay. All right. Well, there you go, Jordan. I mean, at least you're thinking 2 steps ahead of anybody else who's talking about terraforming. Good for you. Mm-hmm. All right, here we go.
By the way, if you have good geoengineering, you might find a way to stir up the Martian core so that it can then generate another magnetic field. I mean, what's stopping us?
Right.
Yeah, Earth gets its magnetic field from our iron core.
From the iron core that's spinning inside of us.
Yeah. Inside of that has this moving iron, which is conductive. And when you have a conductive moving material, it can generate currents, and currents generate magnetic fields. So Mars, that's all stopped long ago. But why not, if we can control planets, go stir it up again.
Right. See, Mars, that's why nobody finds you attractive. Because you don't have a magnetic field.
Oh, just don't.
I just made that up. Come on, man.
Okay, all right. You don't have to test it on this program. Go to open mic night and see how people do.
Oh, my God. Damn! Oh my!
Boy, that was
damn!
that was a good comedic dig, though.
Oh my goodness! Damn!
Chuck is wiping away his tears.
Oh man, because you got me with that one, man. That's oof. You ain't got to test it out here.
Test it out on my show.
Oh God. Oh man, I need some Visine now. Jesus. All right, here we go.
All right, Chuck, we got to take a quick break.
Oh, okay. All right.
We'll come back to segment number 3 of StarTalk Cosmic Queries. Grab bag. Be there. All right, we're back. StarTalk Cosmic Queries. Chuck, you're tweeting at Chuck Nice Comic.
Yes, thank you, sir. That's correct.
I do indeed follow you. I don't follow many things. I follow you. Just let you know.
Well, that's great. I followed you first, so it's not a competition.
I can't top that. Sorry.
There you go.
All right, what are the questions you got for us? We got one segment left. Let's see how many we can squeeze in.
Let's see what we can do here. This is Abhinav Yadav. Hello, Dr. Tyson and Sir Nice. I'm excited to be asking my very first question. Now, you have spoken about moon disrupting observation time.
Oh, yeah.
Are there places in the solar system that are much better for it, where this doesn't exist, somewhere we can just send telescopes and observe? Love the show.
Yeah, that's there's a lot going on in that question, so let me just unpack it briefly. So first of all, the full moon at night is crazy bright. In fact, it's something like 6 times brighter than a half moon because of the way the laws of reflection work.
Okay.
You think it'd only be like twice as bright? It's like even brighter. So on a moonless night, the unaided eye can see a couple of thousand stars. If the moon is out, you can see a couple hundred stars. So it drops it by a factor of 10. So if you're trying to see the deep universe, we have what's called dark time at telescopes. And it's highly competitive to gain access to a telescope while the moon is not up. Okay, it's called dark time. And people who are on the brink of the detection of things will ask for dark time. So then we learned, well, why be on Earth at all? Why? Okay, but if you go into orbit, the moon is still there, okay? Now, the sky is not as bright, but it's still kind of, you don't want to look near the moon. You have scattered light into your telescope beam. So how about 1 million miles on the other side of the moon? How about that? Well, that's where the James Webb Space Telescope is going.
Oh, cool.
Ooh. There you go. Yeah, so it's far away from Earth and from the moon. And so, yeah, we're doing our darndest to get rid of the interference that we're now experiencing. But let me stay at it. There's radio interference, and we have radio wave telescopes.
Right.
So what are we going to do about that? There's all this talk. Whole conferences given unto putting radio telescopes on the far side of the moon.
Wow.
Because the moon only shows one face. So if you're on the far side, you will never see Earth ever.
Right.
Okay, so that famous photo of Earthrise over the moon by Apollo 8, okay, Earth doesn't rise on the moon.
Right.
It never does. It's either always there or never there, because you're either on the side of the moon that faces Earth or the side of the moon that faces elsewhere. And so the reason why that's called Earthrise is because they were orbiting the moon. And when you're orbiting, then the sky rises and sets, and so they caught the rising Earth on the lunar landscape. So it's legitimately Earth rising. It's just highly misleading.
Right.
That's all.
It's like Moon Haiti and Moon Dominican Republic. So just same island, just one side is Haiti and the other side is the Dominican Republic.
Is that really the first? I'm talking the universe here, and you're talking geopolitics?
Man, I need a vacation.
That's evident.
I'm really just thinking about tropical places, that's all.
That's right, but they are the same island. Somebody just cut a line right down the middle.
Cut a line, that's it.
Right,
all right. Well,
so we are thinking about that, and it is a big problem. And so wherever the electromagnetic spectrum is noisiest, we try to do our darndest to avoid it. And sometimes it means going into space to the far side of the moon and even into deep space itself.
Wow. Cool, man.
Yeah.
All right. So, okay. Now, what probe just got out of our solar system And will we be able to receive? So I'm just thinking about telescopes.
Oh, you're talking about Voyager.
Voyager.
Yeah.
Will we be able to retrieve any information from that?
We have what's called a senior review of projects that are growing long of tooth, that have been going for a while. Even if they're giving trickles of data, you say to yourself, it costs this much. What is the incremental knowledge we're gleaning about our state of the universe relative to this new project that is looking for seed funding to discover something new and exciting? And so sometimes you got to turn off the switch. Voyager, we turn off the switch after it exited the influence of the sun. There's everyone thinking, oh, the solar system ends at Pluto or Neptune. No, solar system keeps going.
Right.
All right. And one way to think about it is, as long as you're near enough to the sun to feel its sort of magnetic field and other effects, you say, I'm part of the solar system.
Right.
But the galaxy has a magnetic field also.
Right.
So if you start getting farther and farther away from the sun, the strength of the sun's magnetic field drops, and the strength relative to the strength of the galactic magnetic field. You reach a point. Oh, by the way, it's not just magnetic field, but the particle stream emanating from the sun relative to the ambient particle stream in the galaxy. You reach a point where you can no longer tell the difference between those two. Bada bing, you've left the solar system.
Cool.
Yeah.
All right.
That's how you think about that.
All right. That's how you think about it. All right. Cool.
That's how we roll.
And since we're talking telescopes here, when you talk about observation time earlier, if you're an important...
Well, are you asking a question now?
No, this is still Abhinav. Yeah.
Okay, I was just, because you got to become a Patreon member if you're going to ask me a question. That's all. I'm just checking. Go on, because you got all the data there. So
yeah, I'm also lying, but hey. No, here's what I want to know: if you're an important scientist, do you get bumped up in your request for observation time? Are they just like, Jimmy, please, you're really? That research, get out of here.
Yeah, your seniority has nothing to do with it.
Ooh.
It's how brilliant is your idea. And that's why on our research papers, we don't put your earned degrees next to your name. All right. So an undergraduate, one of these sort of precocious research interested graduate students could have their name right next to someone who's highly senior or even a Nobel laureate. No degrees are put there. No such distinctions are made.
Oh my God! It's the masked physicist. I love it. Instead of the masked singer, it's the masked physicist.
Yeah. So we don't, and I think that's one of the that's an important feature of the entire enterprise. Now, if you have an idea that's a little crazy, that it's not getting past any reviews, the director of the telescope has what's called director's discretionary time. And they can say, I want to give this a shot.
Oh, wow.
And they can grant the time, and it won't have to go through the peer review to be given the time. Oh. But ultimately, the research you do based on it would have to be peer reviewed if you're going to publish it.
Okay. That's a great system, by the way.
And it is. And by the way, the very famous Hubble deep field, do you know that picture that has just galaxies in it?
Yes, it's beautiful.
And there's a couple of stars, but everything you might think is a star is an entire galaxy.
Yeah.
That was allocated on director's discretionary time.
Okay.
And it became one of the most significant images ever taken by the telescope. And you know who received that director's discretionary time?
No, who?
The director. He gave it to himself.
No!
Yes.
Get out!
Yes.
Oh, that's tremendous.
Yes. Is that badass?
It was like, you know what, man?
That's gangster.
I want to look out into nothing.
And there's nothing you can't stop.
Why would you point the telescope that way? There's nothing there. Because I can. All right? I'm the director. I'm the HDIC, the head director in charge. Biatch. Okay.
So the funny thing is, you're absolutely right. The Hubble Deep Field was a spot on the sky that was the least interesting spot you can possibly find. There were no interesting stars, no previously discovered interesting galaxies, black holes, nothing. And he says, let me take the most potent, powerful telescope in the world and aim it there and hang there and let those meager photons accumulate. And let's see what's lurking in the dark. Thus was born the Hubble Deep Field. It may have been the most significant image taken by the telescope itself. And so we allow for that kind of creative thinking that might not otherwise get through.
That's, by the way, what a great story.
I love my people. These are my people.
I mean, seriously, that's probably equally as exciting as the discovery itself. All right. This is Dale Buin. And Dale says, hey, Neil, photons don't experience time. They don't ever decay. Would they decay? Wait a minute. Would they decay if they did experience time?
Yeah. So decay means you are this form of matter in one moment, and later on you're a different form of matter, and you can time that out, and there's usually some variance there, but there's a very tight average that we give for, like, it's called the half-life of, for example, carbon-14. Any radioactive element has a half-life. Well, if all the atoms know that they're supposed to convert within some statistical time frame, then they must have a measure of time. There must be some kind of clock going on within them. All right. Photons moving at the speed of light, time stops for them. So if you have no measure of time, then you cannot know to turn into anything else later in life, because there is no later. If photons did happen to experience time, it means they would not be going at the speed of light, okay? And they would not be pure energy as they currently are, and then they would have the ability to transform into another kind of particle.
Wow.
Yeah.
That is so trippy, man. Oh my God, that is so trippy. Okay.
Because they would know how to keep time. And if you know how to keep time, you would have some clock, and you say, you know, in 1 year, 5 years, 3 seconds, a tenth of a second, I'm going to turn into another particle. Now, just because you have a clock doesn't mean you will turn into another particle. The other conditions have to be right. But if you don't have a clock, there's no reason or understanding we possibly have for why you would change into another particle.
Okay. So photons are super gangster. They're like...
So it means the photon that we detect here that was emitted in the early universe shortly after the Big Bang, as far as it's concerned...
It's still the Big Bang. Hey, let me tell you something, man. I'm a photon. I don't ride or die. I ride and die. I take the ride and then I die.
Always dying and always living at the same time.
Yeah.
So it is detected in the same instant that it is emitted.
Right.
According to the photon itself. So
that's amazing.
It's fascinating. So life as a photon is, like you said, it's a trippy thing.
Wow.
Yeah.
God, I love science.
Yeah.
I mean, that is just amazing. Okay, let's get another one in here.
Yeah, maybe we can slip in another one. Yeah.
Okay, this is Nicholas Lenson. And Nicholas says, hey, Neil, hey, Chuck, given that the black holes lose mass slowly but thoroughly until they no longer exist, would there be a point in time where the mass of the black hole is no longer sufficient to trap light? So the surface of the black hole would become visible. And what would that look like? So wait a minute, did this guy just discover a way to look inside of a black hole?
Any amount of mass, you can calculate how small it would have to be, how compressed it would have to be for it to become a black hole. So if you wanted Earth to become a black hole, you'd have to shrink it down to like the size of a plum. Last I did the math on that. So if you manage to do that, bada bing, you have an Earth black hole. The point is, a lower mass black hole is smaller than a higher mass black hole. If a black hole begins losing mass, it gets smaller and becomes the black hole size appropriate for the amount of mass it has.
Gotcha.
So it's stuck being a black hole.
It's always going to be a black hole.
Correct.
No matter what the mass is, now that it has collapsed into a black hole, it can't be anything else. So
Correct.
if it continues to lose that mass, it will always maintain the properties of a black hole because it can't be anything else.
As it shrinks down. That's right. Now, if for some magic force of nature, the black hole evaporates according to Hawking radiation, which your guy clearly knows about, and somehow did not get smaller, there would be a point where the density would no longer allow it to be a black hole, because it's about the density, it's not about the mass.
Right.
The density would know, and then the black hole would slowly reveal itself as a solid object.
Ah, look at that.
So yeah, it was a great question. And if one day we could manipulate the laws of physics, then we could reach into a black hole, somehow prop up its shape, so that as it got less and less mass, the density would drop, and then we could reveal what's inside. But then at that point, you're no longer looking inside a black hole, are you? You're just looking at a regular object.
Right.
Yeah.
Because you really need that mass down to that small density in order for it to be a black hole.
And you know what happens? As the black hole continues to evaporate, the energy range that gets emitted becomes higher and higher and higher. So large black holes are emitting like radio waves, and smaller black holes will emit visible light. The tiniest of black holes will emit gamma rays. Okay?
Wow.
And it has to do with the size of the black hole, whether the wave that it emits can fit inside the black hole or not. That's the quantum physics of it. Hawking worked all this out. Point is, as it gets smaller and smaller and smaller and smaller, the very last bit. Oh, by the way, as it gets smaller, the rate at which it gives off energy increases.
Gotcha.
Okay, so this becomes a runaway process where it gets smaller and smaller, faster and faster and faster, and the very last moment it happens catastrophically, and you get a little burst of gamma rays.
Wow.
So the original Hawking radiation paper prompted people to look for little bursts of gamma rays, like in the universe, which could signal black holes dying, having completely evaporated.
That is amazing.
Yeah.
Okay.
Now, we do see bursts of gamma rays, but they don't match the spectrum of a dying black hole. But there it is.
Wow.
This is our universe we all live in. It's a beautiful place. All right, Chuck, that was fun. This is another StarTalk Cosmic Queries. Just questions from Patreon members. It was a grab bag. And I want to go back to Galactic Gumbo. I want to hear you imitate it.
That's on board. Get on here, put it together, little Dr. Tyson. Let it know, guarantee. Galactic.
I missed that.
I missed it too. I love it.
We can't call it a grab bag. We'll figure it out on the next time out. All right, dude. Good to have you always.
Always a pleasure.
All right, this has been StarTalk Cosmic Queries. As always, Neil deGrasse Tyson here, bidding you to keep looking up.